Hi everyone. I'm going to go over some of the data analysis for Lab 3. This is a two-part series. One part is in R. I'm going to, that's this video. Another part is in Excel. That's the other video. And what we're going to do is do the analysis for this fake data set you could see here on my website page. So this data set quite is slightly different than what you'll use. The sieve sizes are different. Uh, the second column here is the average size in class, so you can see some example results from calculating average size in class. So this 82.158 is calculated from both the 90 and the 75 millimeter size, and the pan has that other calculation since the pan, the smallest particle size approaches zero, so we do something a little different. Then we're given the percent in class for each screen. So this is the fraction of the total material that stayed in that screen after shaking. And then we have the fraction retained, which is cumulative, and the fraction passing. And what we're going to do is fit the Rosen-Ramler and Gauden-Schumann equations to this fraction passing value versus sieve size. So sieve size is on the x-axis, fraction passing is on the y-axis. So let's look at this lab. If we scroll down, we'll get to the equation sheet. As you remember from class, what we're going to end up doing is we're taking the Gauden-Schumann and Rosen-Ramler equations and we turn them into a linear equation, and that's why we have these. We use log x versus log y plots. And we have equations for finding the fitting parameters here. What we're going to end up using though is this relationship for covariance and variance, as well as estimating the intercept here based on some data. But it's going to be much simpler in R. So we have the sample code here. For the most part, all you have to do is copy and paste it. Certainly don't retype everything. So what I'm going to do is copy. Now if you're watching this video before you've installed R in RStudio, down here you need to install R, which is the language, and RStudio, which is how we're going to interface with R. You can interface with R over command line, for example, but that's much more complicated. So after you install R in RStudio, open RStudio and make a new R script. So then we're going to copy that code, that first set. So this is for the example that's in the lab sheet. We need to convert this to our data. So these three lines here are all you need to change. The rest is copying, pasting, and then reading off the results and interpreting them. So I'm going to put this side by side with the data set here. Let's see if I could zoom in. All right. So the X, that's our sieve size, right? And we're not log transforming it yet. The first entry in X has to correspond with the first entry in Y. That's row-wise for the fraction passing. Otherwise, order doesn't matter. But I would just start with the first row and go all the way down. But actually, don't start with the first row. So the first row here is 100% passing, or the entirety, 1 is passing that screen. That's not really a data point. It doesn't tell you anything. If we had a sieve that had 2 footholes in it and we said 100% is passing, that really doesn't tell us anything. So that data point isn't important. Let's forget that data point. And the same thing with the pan. We're not passing anything through the pan. So this also doesn't tell us anything. So the rows we're going to work with is row 2, 3, 4, 5, 6, 7, 8. These are the only data points we're using for this fit. So starting with row 2 here at 75. I'm going to just delete all these. So input the size, the sieve size in millimeters. We're not doing the average size here, we're doing the fraction passing a certain size. So 75, 19, 4, 1, 0.6, 0.125, and 0.063. All right. Now we're going to input what fraction passed each size. So that's the fraction passing corresponding. So here we have 0.953, and each entry you separate with a comma. Spacing doesn't matter. 0.809, 0.602, 0.427, 0.356, 0.22, and 0.158. All right, let me move this over a little. So you can see everything here. A little bit about R. Spacing doesn't matter so much. This arrow, it's just a less than and then a dash. That's kind of like an equal sign. And then here's a variable name, X and Y, and username. So the last thing you have to do, the last piece of code you have to change is where it says your name here, put your name. So I'm going to put my name. All right, and that's all the code you have to change. We've got X and Y. So let's go back to the lab. So we've made these substitutions after opening up our R script file. So this is like the raw data. Now remember, we have to transform the Gaudian-Schumann equation into a line. In order to do this, we take log of x and log of y. Make sure you get all the code here, parentheses and all. So now we're going to be able to use our fitting equations to find log of x and log of y. Then let's find m. So after transforming x and y, m for the Gaudian-Schumann equation is just the covariance divided by the variance. So while if you're doing this by hand, you have to take products, or maybe in Excel, and you could do that here, but this is much simpler to do. And then this line here where it just says m, that's going to print it to the console. So what we're going to do, we're just going to highlight everything, hit Control, hold down Control and hit Enter, and it runs all the code. And just putting m there, it prints what we calculate for m. So you're going to need this value, this 0.252 in this case, for your analysis, and that's M for the Gauden-Schumann equation. Now we do the same thing for K. Copy this. So we, after subtracting and transforming back, taking the exponential of ln of k, that's what this code does. We take the means, use the linear regression equations, and then solve for k for the Gauden-Schumann equation. In this case, it's 48.12. Now, this is interesting. Let's substitute k in for x in the regular Gauden-Schumann equation. And what do we get? We get 1. So when x is equal to k, that's the size at which 100% is passing, right? We'll talk about that a little more too. All right, now for the Rosen-Ramler equations. First we need to, I'll copy this over. So looking at the Rosen-Ramler equation, we do a little bit more of a log transformation and shuffling things around to get this to be a linear equation, where we still end up with m times ln of x minus m times ln of r in this case. And I'm saving the m this time as rr.m to kind of differentiate it. So we need to transform the initial y in a little bit of a different manner. And that's what this code does, as well as calculate m for the Rosen-Ramler. So m, using the Rosen-Ramler fit, is 0.395. You're going to need to write that down. And r, calculating r, it's like the intercept in the linear equation. Just copy and paste it. Looks like all the parentheses and everything are there. Highlight it, hit Control, hold it down, and then enter. So r is 4.7569. Now let's do a similar analysis to what we just did with the Gauden-Schumann equation, replacing x with r, the size with r. Well, that's 63 or 0.632 or 63.2% passing. So this number is actually consistent, and it's based on just the mathematical properties. So r, if you know r, you know about 2/3 is passing that value. All right, so we've got m and r for Rosen-Ramler, as well as m and k for the Gauden-Schumann equations, and we've written that down. Last thing, you can either plot, make the plots by hand on these pages in the lab, or you can copy this code here. It's a good bit. I've included it here just for documentation purposes, but it's much easier to copy and paste it here. I put it on my site. So highlight it all. And then just Control C, Control V. Last thing, before you run this code for the plots, you need to save this R script, and then it's going to know where to save the plots. It'll end up generating a PDF file of the plots. So hit save, I'm going to go to the desktop and save it in this lab 3 folder. Shouldn't matter. I'm going to say lab 3 analysis .r. Hit save. Then I'm going to go to the top here, make sure everything's highlighted so it kind of runs everything fresh. It'll save your variable values, but highlighting it all, holding control down, hitting enter, and it makes both of our plots. So let's take a look at the plots. If we go to my desktop here, it'll save the plot with your name, last first, Gauden-Schumann and Rosen-Ramler. So here we can see when we transform the x and y axis, it's just we're fitting a line. All right, and down here it'll say k is 48.124. Now we can see from this dotted line that that lines up with the entire fraction passing. Now we didn't actually observe that, right? It's a larger size, but according to this fit, 100% passing, if we try and remove some of the error, is this value of 48.12. So that's an interesting property of the Gauden-Schumann equation, is you can actually get above 1 on the percent passing, and that might be something to mention for some of the discussion questions. Now let's look at the Rosen-Ramler plot. We have the same thing, the transformed x-axis and the transformed y-axis, and a linear fit. Here we can see r, the intercept, is 4.76, and that intersects with that 0.63 number. The other thing to keep in mind, m, has to do with the slope. Right, we're multiplying the intercept of r, log of r, natural log, by m, but it deals with the slope. So m will tell us kind of how steep this fit is, or how it really tells us how the size distribution changes as we change sizes, how the fraction passing changes, right? While r and k are kind of like the intercept, but then they, because of the transformations, they correspond to different values for percent passing based on the fit. All right, if you have any more questions, let me know. These plots by themselves can be turned in with the lab as your work. If you go this route, you can include the R script as the proof of your work, but I'll end up only looking at it if there's problems with your plots. Any questions, feel free to get in contact me. All right, thanks everyone, and I'll see you for the next video.